So in the last video, I started infinite series and defined infinite series and explained the convergence of infinite series, and also I explained by taking some examples when the series converges, diverges and oscillates. And in this video, I consider one standard series, that is geometric series. I explain the convergence of that geometric series, and then Cauchy's general principle of convergence, and if possible I start positive term series first. Positive term series. How to define a series? Suppose UN is a sequence. UN is sequence. What do you mean by sequence? Sequence means it is a function from set of naturals to reals, and sequence is denoted by writing its nth term. A sequence, any sequence is denoted by writing its nth term. Sequence may be denoted by Sn, Un, An, Yn, Tn and so on. Now, if Un is any sequence, then the sum U1 plus U2 plus U3 plus etc. Un plus etc. to infinity, this sum is called infinite series. Infinite series. And the meaning this since there are number of terms is infinite, the term itself has no meaning. Sum of the infinite term in it has no meaning. Therefore, to give the meaning for this, we define when the series converges. Definition. When do you say that series converges? We consider sequence of partial sums Sn. Defined by Sn is U1 plus U2 etc. Un. Sn is U1 plus U2 plus etc. Un. Then, if this sequence converges, then we say that the series converges. If Sn sequence of partial sums, how it is defined? Sn is U1 plus U2 up to Un only. This consists of infinite terms. But we take Sn as only U1 plus U2 up to Un. We form a sequence. What is that sequence? U1, second is U1 plus U2, third term is U1 plus U2 plus U3 and so on. This sequence Sn is U1, second term is U1 plus U2, third term is U1 plus U2 plus U3 and so on. Nth term is this. If this sequence converges, then we say that the series converges. Series converges. That I explained in the last period. Now, I consider this standard problem here. Examine the convergence of the geometric series sigma r raised to n minus 1. Of course, n is 1 to infinity, sigma r raised to n minus 1. Or equivalently, prove that the geometric series sigma r raised to n minus 1 converges if mod r is less than 1, and diverges if r is greater than or equal to 1, and oscillates if r is less than or equal to minus 1. Three cases are there. Equivalently, question may be, prove that the geometric series sigma r raised to n minus 1, n is equal to 1 to infinity, converges if mod r less than 1, diverges if r is greater than or equal to 1, and oscillates r is less than or equal to minus 1. Now, what is this geometric series? Sigma r raised to n minus 1 means 1 plus r square plus etc. r raised to n minus 1 plus so on. This is the geometric series. You have some idea about this geometric series. What is r here? R is common ratio, it is called. If common ratio less than 1, mod r is less than 1, it converges. Now, to prove that, first we consider mod r is less than 1. Now, Sn is the sequence of partial sum is, when do you say that series converges? Series is said to be convergent if the sequence of partial sum converges. Now, what is the sequence of partial sums? Sn is 1 plus r square plus so on r raised to n minus 1. And we have this sum is given by 1 minus r raised to n upon 1 minus r. what is sum to n terms of a geometric series? It is a standard formula. A into 1 minus r raised to n upon 1 minus r. Therefore, it is 1 upon 1 minus r minus r raised to n by 1 minus r. Now, since mod r is less than 1, this r is less than 1, r raised to n tends to 0 as n tends to infinity. Therefore, limit Sn becomes 1 upon 1 minus r. Because this r raised to n becomes 0 as n tends to infinity. Limit Sn becomes 1 upon 1 minus r. Therefore, it is finite. Therefore, the sequence Sn of partial sum converges. Partial sums converges. Therefore, the geometric series sigma r raised to n minus 1 converges if mod r is less than 1. This is first case. Mod r less than 1, sigma r raised to n minus 1 converges. Why converges? Say, we have proved like this. We have taken sequence of partial sums Sn, where Sn is defined by this. Sn is therefore is given by this. And if mod r less than 1, r raised to n tends to 0 as n tends to infinity. So, limit Sn is 1 upon 1 minus r. This becomes 0. Therefore, Sn of partial sum converges. Therefore, sigma r raised to n minus 1 converges when mod r is less than 1. Now, second case is suppose r is greater than 1. Let r greater than 1. We take this as second case. Then r raised to n tends to infinity as n tends to infinity. To follow this one, r greater than 1 means I take r is 2. Then 2 raised to n becomes infinity as n tends to infinity. But if r is less than 1, suppose half, then what happens? R raised to n becomes 1 upon 2 raised to n. It tends to 0 as n tends to infinity. That was the first case. R is less than 1. But if r is greater than 1, then r raised to n tends to infinity. Therefore, Sn is 1 upon 1 minus r minus r raised to n by 1 minus r tends to infinity. This implies sigma r raised to n minus 1 diverges to infinity. Diverges to infinity. Now, case 3. If r is less than minus 1, r is less than minus 1, then r raised to n, for example, I take r is minus 2. R is minus 2. Then what is r raised to n? Minus 2 raised to n lies between minus infinity and infinity as n tends to infinity. If r is minus 2 raised to n becomes even, it tends to positive real number, large real number. N is negative, n is odd, n is even, it becomes positive. It tends to r raised to n tends in this direction, positive direction. Suppose n is odd, r raised to n tends to negative direction when r is negative and less than minus 1. Therefore, r raised to n tends to infinity or minus infinity. Hence, sigma r raised to n minus 1 oscillates infinitely. Because this Sn oscillates, correspondingly r raised to n oscillates. Sigma r raised to n minus 1 oscillates. Now, suppose r is equal to 1. Next case, r is 1. Then Sn is u1 plus u2 plus etc. un becomes, what is Sn? Because series is sigma r raised to n minus 1. It is 1 plus r square etc. so on. u1 is 1. u2 is, what is u2? It is also 1 plus 1 plus 1. This is n. And this tends to infinity. Say, when r is 1, sequence of partial sums becomes u1 plus u2 un becomes n only, and it tends to infinity. So, the sequence of partial sums diverges to infinity. Hence, the series diverges to infinity if r is equal to 1. Now one case is left. What is that? R is minus 1. R is minus 1. If r is minus 1, then Sn is sequence of partial sums. R is minus 1, then what happens? It becomes 0 if n is even and 1 if n is odd. Because what is Sn? Sn is 1 plus r square etc. plus r raised to n minus 1. And what is r minus 1? Suppose n is even, you will get 1 plus minus 1, 0. N is odd, you will get 3 terms, S3. 1 minus 1 plus 1. You will get 1. Therefore, when r is minus 1, Sn, the sequence of partial sums, only 2 values it takes, 0, 1, 0, 1, 0, 1. And it oscillates finitely. Unlike in the case of r is less than minus 1, in that case what happens? When r is less than minus 1, Sn oscillates infinitely. It takes the values from minus infinity to infinity. So when r is less than minus 1, sigma r raised to n minus 1 oscillates infinitely. So the series oscillates infinitely. When r is equal to minus 1, it oscillates finitely. So these are the cases. So finally, what happens? Say this is the summary here. Sigma r raised to n minus 1, a geometric series, converges if mod r less than 1, diverges if r is greater than or equal to 1, and oscillates finitely if r is equal to minus 1, and r is less than minus 1, it oscillates infinitely. Equal to 1 also, it diverges equal to 1. This is the geometric series. We may refer this series or we may refer this result, that is convergence of geometric series, in some next topic. Now one example on this geometric series. Prove that the series sigma 1 upon 4 raised to n converges to 1 by 3. Sigma r raised to n 1 upon 4 raised to n converges to 1 by 3. Here Sn is, what is Sn? Sigma 1 upon 4 raised to n is, it is of the form sigma r raised to n minus 1. R is equal to 1 to n here. R is or n is equal to 1 to infinity. Sigma r raised to n, n is equal to 1 to infinity. Correct? What is R? R is 1 by 4. Therefore, sequence of partial sums, convergent, it is convergent, you can directly say. Why it convergent? Because it is a geometric series which R is 1 by 4. So mod R less than 1, therefore it converges. By using above theorem or above discussion, geometric series converges if mod R is less than 1. Here R is 1 by 4, that condition is satisfied. Less than 1, therefore it converges. Now to find the limit, what is Sn? A is 1 minus r raised to n minus 1, 1 minus 1 by 4 raised to n minus 1 divided by 1 minus 1 by 4. Correct? 1 minus 1 by 4. A into 1 minus r raised to n minus 1 by 1 minus r. It is, what is this? It is is it correct? 1 minus 1 by 4. Yes. It is 1 minus 1 upon 4 raised to n minus 1 divided by 3 by 4. Correct? 3 by 4. A is there, A is 1 by 4 here. So just a minute. What is Sn formula? A into 1 minus R raised to n minus 1 divided by 1 minus R. This is the formula for sum to n terms of the geometric series. So 1 by 4 into this. So 1 by 4 into this. So 1 upon 3 into 1 minus 1 upon 4 raised to n minus 1. 4 raised to n minus 1. Sum to n terms means n is 1 minute. Sigma 1 upon 4 raised to n means, just a minute, sigma 1 upon 4 raised to n is always 1 to infinity. N stands from 1. Or if here n can take 0 to infinity or 1 to infinity. If you take 1 to infinity, what is the first term? 1 upon 4. And you will get A into 1 minus R raised to n minus 1. Yes. What is R? 4 raised to 1 upon 4 raised to n minus 1 upon 1 minus R. It is correct. Say geometric series. What is the sum to n terms? Sum to n terms is A into 1 minus R raised to n minus 1 by 1 minus R. Is it correct? A into 1 minus R raised to n upon 1 minus R. What is sum to n terms? Just a minute. A into 1 minus R raised to n, not, sorry, A into R raised to 1 upon 1 minus R. Correct? A into R raised to n minus 1 is, that is nth term. This is formula for Tn, nth term. But sum to n terms is this, 1 minus R raised to n upon 1 minus R. So, as n tends to infinity, Sn is, it is 1 by 3. Sn is 1 by 3. Therefore, this 1 upon 4 raised to n converges because from this, and converges to which value? 1 by 3. Because the sequence of partial sums, Sn, how it is defined? Sn is 1 by 4, 1 by 4 square, 1 by 4 raised to n. 1 by 4, 1 by 4 square, 1 by 4 raised to n. And what is sum to n terms of geometric series with A is 1 by 4, R is 1 by 4? It is 1 by 4, A into 1 minus R raised to n upon 1 minus R. So, the sequence of partial sum converges to 1 by 3. Therefore, the given series converges to 1 by 3. This is one example for the previous article. Now, what is Cauchy's sequence? Next is Cauchy's general principle of convergence. Cauchy's general principle of convergence, or it is sometimes called Cauchy's criterion. Cauchy's criterion. You have studied Cauchy sequences, and that is this Cauchy's general principle of convergence based on Cauchy sequences. Here, while defining convergence of a series, we have associated a sequence of partial sums. If the sequence of partial sums converges, then the series converges. In the definition we have used sequence of partial sums, but always it is not possible or convenient to construct a sequence corresponding to the series. It is difficult to construct the sequence of partial sums. In that case, this is very helpful. Now, it states like this: the series sigma an is used here, 1 to infinity, converges if and only if for every epsilon greater than 0, there exists a natural number p such that mod am plus 1, am plus 2 plus etc. plus an less than epsilon for all mn greater than or equal to p. This is called Cauchy's general principle of convergence. Understand this we use when it is difficult to form a sequence of partial sums. We directly apply this Cauchy's general principle. Proof is based on Cauchy's sequences. Cauchy's sequences. Now, what does this Cauchy's general principle of convergence states? A series sigma an converges if and only for every epsilon greater than 0 there exists p natural number, so that mod am plus 1, am plus 2, an less than epsilon for all mn greater than or equal to p. Now, to prove this one, we know that the series sigma an converges if and only the sequence of partial sums I take this as Sn converges. Now, by the Cauchy's criterion for convergence, a sequence Sn converges if and only for epsilon greater than 0 there exists a natural number p such that mod Sn minus Sm is less than epsilon for all mn greater than or equal to p. Correct? For all mn greater than or equal to p. That is, what is Sn? Sn is a1 plus a2 plus etc. plus am plus 1 plus etc. plus an. It is Sn. Minus what is Sm? Sm is a1 plus a2 plus etc. plus am. It is less than epsilon. For all mn greater than or equal to p. Therefore, say up to am cancels. We get mod am plus 1, am plus 2 plus etc. plus an is less than epsilon for all mn greater than or equal to p. Therefore, a series sigma an converges if and only for epsilon greater than 0 there exists a natural number p, so that for all mn greater than or equal to p, mod am plus 1, am plus 2, an is less than epsilon. I think the proof all of you understood. Proof of this one. The theorem directly based on Cauchy's criteria for convergence of sequences is based on that one. Now, this Cauchy's general principle of convergence is helpful when it is difficult to form a sequence of partial sums. See, next topic is series of. First, we start with series of positive terms. We study some theorems for the convergence of series of positive terms, and then we consider absolute convergence, and that's tests which are applicable for positive term series is applicable for negative term series also. That is a second topic. Next is alternating series. Alternating means some terms are positive, some terms are negative. That is a separate topic. But this series of positive terms, it is a major portion of this series in your syllabus. Here we study 4 or 5 tests for convergence. We do not for the sequence of partial sums also. We have sequence of partial sums is only definition it is. Definition for a series to converge. But for test the convergence we have different tests. They are very helpful to test the convergence. Let us consider that in the next video.